In this section, I'll talk about the implications of removing human drivers from automated vehicles on safety. The poster child for the potential for software inside vehicles to have defects that result in deaths is the Toyota unintended acceleration story. At one point, that phenomenon was blamed for killing at least 89 people and was associated with thousands of customer complaints. The details of that story are long and complicated, but in the end, Toyota admitted to at least faulty floor mats and sticky accelerator pedals causing at least some of the problems. Nonetheless, in the press, what was said was it was all the driver's fault. While there have been hundreds of settlements since all that happened for drivers who believed that something inside the car caused a significant injury or even death, Toyota has never admitted that there was a software defect that caused a problem. Rather, the standard story has been that some driver pressed the gas pedal instead of the brake pedal, causing the problem. If you want to know more about what really happened, there's a link at the bottom of the page that tells the other side of the story. More recently, there have been a number of fatalities associated with the use of the so-called Autopilot feature in Tesla vehicles that have resulted in legal action. In this case, some of the questions include whether or not the driver monitoring capability of the vehicle is adequate, and in general, whether or not the demand made of the driver to remain in charge of safety is within reasonable human capability limits. As with Toyota unintended acceleration situations, Tesla blames the driver for not paying attention or for otherwise not avoiding fatal crashes. About a decade after the Toyota unintended acceleration allegations, there are similar allegations against Teslas, in this case, driving through the wall of a house. To be sure, at this point, nothing has been proven either way, but regardless of what the root causes turn out to be, it is clear that the car industry's strategy is to always blame the driver if it's possible. This strategy is supported by the U.S. government, who blame 16,000 unintended acceleration cases on drivers every year. It's worth noting that in a typical government investigation of an unintended acceleration claim, driver error is considered as a possible cause, but software defects are typically not even considered as a possible cause in the investigation. In other words, if a car runs just fine during testing, then the conclusion is it must have been driver error, without ever actually digging in to find out whether it's plausible that a software defect caused it. In this talk, we're not going to be able to resolve the issue of what's really going on here. However, I will make the observation that the uniform playbook across the decades has been, unless there's evidence that is not only irrefutable, but very easily repeatable, what you tend to see is that the driver is blamed for any odd, dangerous behavior of a vehicle, even though that could possibly have come from a software defect. As vehicle automation capabilities have been deployed, the industry has doubled down on the narrative of blaming the human driver. Videos of people falling asleep in cars that are not fully automated abound on social media. Crashes of automated vehicle test fleets are blamed on drivers falling asleep or drivers not paying attention and safety drivers being distracted. The industry narrative is that humans are the ones making the mistakes on the roads and that automation will prevent those mistakes. The U.S. government, Department of Transportation, NHTSA, National Highway Traffic Safety Administration, has famously said that 94% of all serious crashes are due to human error. They've also restated this in forms such as 94% of serious crashes or fatalities are due to human drivers making bad choices, and so on. Even though that number comes from a U.S. government study, that's not actually what the number means. So let's ask, where did that 94% come from? If you read the study that's being cited, it says the critical reason was assigned to drivers in 94% of the crashes. Well, critical reason doesn't sound quite the same as human error. Let's read a little more. In the very next sentence, in that same report, it says, however, in none of these cases was the assignment intended to blame the driver for causing the crash. Well, what's going on here? First of all, this document is a restatement of a more extensive study that pushes even further away from blaming the drivers for 94% of the crashes. What's happening here is, sure enough, in some cases, the human driver probably did cause the crash. But in a lot of cases, something else went wrong, and the human driver might have been able to prevent it but did not, or the human driver contributed partially to other circumstances that caused a crash. This means that if you try and make the normal conclusion that, well, if 94% of crashes are human error, then automated vehicles ought to be 20 times better if they don't make human errors, that's a false narrative. Let's look a little deeper at what's really going on. 74% of the human driver errors were recognition and decision errors. While some of them are likely errors that an automated system would not make, things such as perception not being 100% accurate are definitely going to be an issue with automated driving systems just as they are with human drivers. Also, the software driver has to handle the 6% of no kidding there was no driver involved crash causes, things such as tire blowouts and brake failures and drivetrain failures. So when you see the 94% statistic, that does not necessarily mean that automated vehicles will be 20 times safer than humans, because even the data cited does not support that conclusion. And as we'll see in other parts of this talk, in fact, it's probably going to be a lot harder than that to make automated vehicles as safe or hopefully safer than human drivers. Even if you want to believe that there's a lot of truth in the 94% of crashes are due to human mistakes claim, which, as we've just discussed, isn't really quite what that statistic means, the other side of that coin is that people are actually pretty good at preventing most crashes. Let's take a look at some of the big issues that have happened. For Toyota uncommanded acceleration, in fact, most of the complaints were saved by the human, regardless of what the cause might have been. As of May 2010, there were 89 deaths and 57 injuries attributed to the phenomenon, but there were more than 6,000 complaints. And a typical such complaint is some driver says it happened to them, but they were able to recover the situation and avoid death or serious injury. Another problem was General Motors having brake issues. There were no deaths reported. There were 293 injuries. There were 2,000 crashes, but almost 11,000 complaints. The idea here is that even if you have a defect in the vehicle, human drivers are really good at compensating for unexpected behaviors regardless of the cause. This leads us to a question. If you put in an automated driving system on a vehicle that might have defects inside the vehicle, will the automated driving system be as successful at fault mitigations as the human drivers? Sure, humans on occasion make mistakes, but they're incredibly good with dealing at heavy-tail, weird issues that aren't supposed to happen, but nonetheless happen all the time in the real world. Part of the driver error narrative is a claim that there are essentially no big life-critical software defects in vehicles, and therefore it's always the driver's fault. That claim has lost a lot of credibility in the past 10 years. If you look at recall data, you can see that a significant fraction of recalls are due to software defects or software integration problems. It's important to note that these are U.S. government NHTSA recalls, which are by definition safety relevant. If it was not safety relevant, there would not be a recall. That's a lot of campaigns for software defects in increasing numbers in recent years as the software complexity of vehicles has gotten higher. There's no reason to believe this trend will reverse itself when automated driving systems, which are even more complicated software than is in current vehicles, become the norm. While it's easy to show aggregate statistics of software recalls increasing, sometimes there's a denial reaction to that number that generally attempts to argue, well, those are safety-critical software defects, but they're really not that big a deal. They have small impact, they won't affect many people, or in general, they're not actually as scary as it may sound. To address that concern, I've done some analysis of the NHTSA recall database and pulled out quite a number of recalls that sound like they could, or in fact in some cases have, killed people. There's a web address there that has the full list of more than 100 recalls in recent years that are firmly related to software in life-critical type issues. I've pulled out a very small fraction of that listing just to give you an idea of the kind of things you see. Going down them quickly, you see vehicles pulling to one side during an evasive maneuver, a fail-safe activation that doesn't stop vehicle motion during Smart Park, anti-rollback software on a truck that caused the truck to move instead of staying still, forward collision avoidance not detecting a stationary vehicle that it is supposed to detect per the manufacturer's specification, regenerative braking failure that reduces acceleration. In other words, you lose braking authority when you're supposed to be braking with regen. A transmission downshift to first gear that causes the vehicle to lose control at high speed. A defect in automatic braking system that not only cancels automatic braking but locks up the wheels at speed. Active lane keeping assistance that does not intervene in lane departure despite its requirement to do so as stated by the manufacturer. And an engine that does not reduce power due to a stability software defect. In other words, it keeps on high power. Other sets of software defects are many, many reports of airbags being disabled so that they do not deploy when they're supposed to in a crash, and a few others where airbags deploy when they should not. Overall, there are large numbers of safety-critical software defects making it out into the fleet and being subject to recall. So these are not speculations. These are things that have been confirmed and the automakers have actively recalled with the deployed fix. The question is, what happens when an automated driver hits one of these software defects in the underlying vehicle? And based on this history of software quality, what basis do we have to believe that the automated driving software will be acceptably close to perfect to trust people's lives with it? Here are some examples of the types of ADS fault handling that will need to be included in a fully automated vehicle. If a tire blows out or wheel becomes detached, the ADS will need to know how to perform a controlled stop or detect that a tire compromise has occurred and switch to whatever degraded mode is required for run-flat tire operations. If there's a failure of the service brakes, the ADS will need to know some combination of downshifting if there's a transmission, switching to all regenerative braking, or if regenerative braking has failed, switching to normal service brakes, applying the parking brake if that's helpful, and especially for a heavy truck, knowing about runaway truck ramps. If there's a catastrophic sensor failure, such as the entire sensor set gets covered in mud or is damaged by some sort of foreign object strike, the ADS will need to know how to dead reckon to a stop using the most recent object trajectories available. If the underlying vehicle has some design defect that results in uncommanded acceleration, the ADS will need to know how to detect that, command de-energization of the engine or motors, and apply forceful brakes to overcome the torque provided by the engine or motors they fail to shut down. If there's a main battery fire, the ADS will need to know how to shed electrical load, bring the vehicle to a stop, and initiate passenger evacuation. The examples on the previous slide are just a handful of things that immediately come to mind when you ask the question, what does an ADS need to take care of that has to do with failures of the equipment other than the ADS itself? A more general way of approaching this is asking how controllability is accomplished when you have no human driver to deal with controlling potential faults. Controllability is a concept in ISO 26262, which is used as one of the factors to determine the automotive safety integrity level, ASIL, of a particular safety requirement. ASILs run from QM to ASIL D as in Delta, but a lot of the lower ASILs are only accessible if you have high controllability. In other words, the own vehicle driver or some other actor in the situation is able to prevent a bad outcome even though some sort of fault has activated. With an ADS, there are two ways to go, and every safety requirement will have to determine which of these two ways or some combination it uses. If you want to claim that an existing vehicle component is only rated at ASIL A or ASIL B because it has good controllability for failures in a normal car, then the ADS will have to exhibit the same controllability to avoid having to change the ASIL rating. For example, if there's a component that when it fails causes something potentially deadly, but a normal human driver would be expected to very easily mitigate the risk, then that component could justifiably have a low ASIL in a human-driven car. But retaining that ASIL imposes a requirement that the ADS has to also know how to control the fault if it should occur. Alternately, if the ADS doesn't know how to control the faults in all the many components that could result in a bad outcome, then those components have to have their ASIL upgraded based on a C3 uncontrollable rating. Upgrading the ASIL requirements for components across the car could mean significant redesign, significant expense. This means when you're converting to an ADS, you need to revisit every single component on the vehicle that has some connection to safety and either upgrade the ASIL so the ADS does not need to worry about it, or you need to understand what it means to mitigate a failure of that component. In other words, what controllability exactly was taken credit for in the safety analysis, and teach the ADS how to exhibit that same level of controllability. In other words, if you remove the human from the vehicle, you're removing a very powerful general-purpose fault mitigator, and the ADS has to either replace it or you need to upgrade the integrity of the components so that the failures fall in line with ISO 26262 requirements. There's an additional challenge if you're adding an ADS to an off-the-shelf vehicle that you may not know all the controllability assumptions that took place when the vehicle was designed. You may not have a set of ADS requirements for controllability because the designers just assumed humans generally do the right thing. But now you need to understand how to teach your ADS to do the same thing when you may not even be sure what those requirements are. Stepping back to look at the bigger picture, we have a situation in which the software in vehicles is not perfect, but contributes an unknown amount to fatalities, with human drivers in charge of both cleaning up any messes that might be caused by vehicle problems and taking the blame if something goes wrong in most cases. People are fond of saying computers won't drive drunk, a nod to the 94% statistic, which we realized isn't really what people say it is. And then they presume that means that automated vehicles will be basically perfectly safe without any real evidence to support that proposition. If you do a little reality check, you find out drunk and DUI is only 28% of the fatalities, so there's still a lot of other things that the automated driving system will have to deal with, even though it doesn't drive drunk. But a bigger issue is automated driving systems are very likely to make different mistakes that people would not normally make, especially perception and classification errors. This technology is notoriously brittle in the face of surprises. I'll show two quick examples of things we've seen. One is a perception system that classifies 5-element traffic lights with a red light on top as a person. Well, this may be humorous and might result in some false stops near the traffic light, and the traffic light's red anyway, so maybe that's not a big deal. But it shows you that they can be pretty easily fooled by things that a normal human would never mistake. A normal human would never mistake that traffic light for a person sitting up on the beam across the road. Now, while that one might seem benign and humorous, some of the other mistakes are a lot more frightening. For example, we saw children next to adults not being seen. During testing, you might not even notice this is happening because the vehicle would avoid collision with the adult person that was seen, but there's a kid next to it. And what do children do? Well, sometimes children run away from their parent and take off, and the vehicle wouldn't even know there was a child there, increasing the risk of something entering the roadway unexpectedly. We cover more of those types of risks in the perception portion of this talk. But the point is that these systems can be brittle, and it's naive to think that just because it's a machine, it will never produce an incorrect output. There will be a non-zero number of automated driving system driver errors, for lack of a better word. These systems will make mistakes. To be sure, there's no requirement that they be perfect. Generally, what you want is the whole system to be noticeably better than a human driver. but they will make mistakes. And the question is, what happens when there's an ADS driver error? It might be an error of commission, that it actively makes a mistake by misclassifying something, or it might be an error of omission in which the underlying vehicle has a fault and the ADS does not know how to clean up the mess properly. A potential issue with ADS driver error is that every automated vehicle crash is a product liability lawsuit waiting to happen depending on the law that governs the location where the crash happened. If you have a design defect in the vehicle automation technology that caused the crash, then that means all the vehicles with that hardware and software combination have the same defect, and it starts looking like a defective product instead of human error. Remember, the whole point of automation is there's no human driver to absorb the blame. So what happens with driver automation problems? While you might think that this problem is still a ways off, ask yourself the question if there's a driver monitoring system that is part of the safety argument for an SAE Level 2 or Level 3 vehicle. In other words, we think the vehicle is safe because we have an effective driver monitor. If there's a defect in the driver monitor system design or software that fails to monitor as it's supposed to, we need to ask whether the vehicle design itself will share blame if there's a resulting crash. This discussion of what the role of the human driver is in not only driving but also managing failures of equipment that may occur leads to a somewhat different view of the role of the human in a vehicle than the traditional SAE levels. This vehicle automation modes chart sets forth the responsibilities of the ADS with a picture of the car and the human with a picture of the person. It involves 4 different modes. It's important to understand which mode the system is operating in at any given time, and when and under what conditions the ADS is responsible for different types of safety. The first mode is assistive mode, in which the human does the driving, is in charge of driving safety, and is in charge of other safety. The second mode is supervised, in which vehicle automation does the driving, but the human is in charge of driving safety and other safety. For a highly automated vehicle in which there's a true ADS that's in charge of all the vehicle driving, there are 2 modes. One is automated, in which the ADS does the driving and is in charge of driving safety, but the human does other safety. And the other is autonomous, in which the ADS is in charge of not only driving, but also driving safety and other safety. It's important, especially for vehicles that have multiple potential different operating modes, for the human driver and the ADS to both agree on which mode the system is in and to make sure that the ADS is in charge of the aspects of safety that the human thinks the ADS is actually in charge of. The discussion to this point has been about driving safety, and this chart makes it clear that when you're in automated or autonomous mode, the ADS is entirely in charge of driving safety, and when you're not, then it's on the human. But what about that other safety column? What's going on with that? Well, the difference between automated and autonomous is whether a human occupant of the vehicle or some remote operator owns other safety, or whether the vehicle, the ADS, also owns it. So let's take a look at the kind of things that might be involved in other safety. One aspect of other safety that goes beyond just driving safety that an ADS will need to deal with in an autonomous vehicle is the safety of operations and human interactions. If you think about it, human drivers do more than just drive. They're responsible for ensuring safe occupant behavior, for passenger safety, for detecting and managing equipment faults, and so on. Here's a picture of a cute kid in a car seat. Well, the kid's in the car seat but not buckled in. So if the ADS is the only thing in charge of safety for the system, the ADS should realize that it's not safe to operate because the child's not buckled in. In the real world, you might want additional rules such as no children under a certain age can ride in a vehicle unaccompanied by an adult. But the point is, we're not talking about driving safety at all. We're talking about different aspects of passenger safety that if you have a fully autonomous vehicle with no qualified driver, you need to have a plan to, for example, keep some parent from sticking their kid into a robo-taxi and sending them off to daycare with nobody accompanying them. There are also operational limits and situations that need to be understood. If the system exits the operational design domain, the ADS needs to understand that, even though some of the aspects of the operational design domain might be quite subtle. What if there's a vehicle fire or a catastrophic failure? What if there's a main battery fire? How does the vehicle detect that and do the right thing, which might include waking up sleeping passengers or arranging for the extrication of drunk passengers who may be passed out in the back seat, but now they need to leave the vehicle because there's a battery fire? In a human-operated taxi, there's a taxi driver who can take care of such things. But in a completely autonomous vehicle, there's just the passenger. That passenger becomes incapacitated. How do you get them out of the vehicle? There's also the matter of post-crash response. All these things can be figured out, and they might well involve remote services helping the vehicle deal with the situation. But the point here is, to be a fully autonomous vehicle, you have to have a plan to make all this happen without a remote operator babysitting the vehicle continuously to keep an eye on things. If a vehicle is to be truly autonomous, it can't have a continuous human babysitter. It needs to figure out when something has happened that requires attention and invoke the attention, just as a human operator would try and fix anything they could and then dial the local emergency number, such as 911 in the US, to get help if they can't. Sure, dialing the number is easy for a car, but recognizing that it's time to dial the emergency number is the tricky bit. Automated vehicles will also need to interact with non-drivers. Pedestrians, potential passengers, especially for robotaxi. How do you know you're not going to take off when a potential passenger has their hand grabbing the door trying to open it? Interaction with police, emergency responders, and so on. All these tasks are directly relevant to safety, but may fall a little bit outside what would normally be considered just driving safely. Another way to put this is that a human vehicle driver is not just the driver of the vehicle. They're sort of the captain of the ship. They're responsible for everything. And when you take the human driver out, the question is, who ends up being the captain of the ship to deal with whatever it is that happens, whether it's something that was designed into the automated driving system or not? Another aspect of other safety beyond driving safety has to do with life cycle issues. There are a number of things that will happen during the vehicle life cycle that can potentially result in unsafe operation. And the question is, how much of the responsibility for either fixing problems or at least noticing that a problem impairs safety is delegated to the ADS versus other mechanisms such as fleet operations? One is handling updates. The ADS will need to make sure it only installs updates when it's safe to do so. But from an organizational point of view, you may need to fully recertify for safety after every single weekly update and make sure that the update is installed properly. You'll also need to decide whether a vehicle will remain acceptably safe if it misses an update for some reason. Security in general will clearly be a problem here. There's also vehicle maintenance. There'll be pre-flight checks, cleaning, snow removal, and corrective maintenance that will need to be done. It's unreasonable to expect an ADS to do mechanical repairs on its own vehicle, but it will probably need to understand that certain maintenance routines need to be done on a certain time scale so it can return to a maintenance facility to have them done. And it may well need to be able to diagnose incorrect maintenance or realize there's been some sort of fault that requires a repair, since if it's fully autonomous, there's nobody in the vehicle necessarily that will even notice something's broken, let alone realize that something needs repair, given that the typical passenger is not expected to be a certified autonomous vehicle mechanic. There are some maintenance items that might seem trivial on a human-driven vehicle that could end up being life-critical on an automated vehicle. As a simple example, consider windshield washing fluid. In a human-operated vehicle, when the windshield washing fluid runs out, a human driver, in the worst case, if mud splashes against the windshield, can stick their head out the window and at least to get the vehicle to a safe stop. But what if there's an automated vehicle that's been designed to assume that the optical sensors can always see because there's cleaning fluid that keeps them clean? That same vehicle pulls out beside a truck in some messy weather, and every optical sensor in the vehicle gets coated with mud. If the windshield cleaning fluid has run out, then that could be a life-critical issue. Even worse, supply chain issues can affect safety. What if the windshield fluid in the supply chain was missing required antifreeze because the wrong type got delivered or there was a quality fade issue in which the supplier cut corners? What if the windshield wiping fluid is a frozen block of ice instead of fluid, and you don't find it out till you're at highway speed passing a truck? Again, a human can usually mitigate these sorts of things, but if the ADS hasn't been designed to handle that situation, it could have a bad outcome. Things such as counterfeit parts, incorrect replacement parts, and so on always present a hazard to a normal vehicle. But if the ADS is not designed to be able to compensate for these kind of failures, even a fairly minor supply chain fault can have a significant adverse life-critical outcome if it hasn't been accommodated in the ADS design. Summarizing the changing role of the human driver, removing the human driver from an automated vehicle is a two-edged sword. There's no human driver to make mistakes, although an ADS will probably make different mistakes. But there's also no human driver present to handle weird stuff and problems that occur, and no human driver to blame for crashes. It's all on the ADS. That means the ADS has to handle vehicle equipment failures, and it has to handle non-ADS software failures that will inevitably occur in these vehicles. In other words, instead of having a human as a general-purpose compensation mechanism to improve safety, all that responsibility now falls on the ADS, driving ADS requirements and complexity far beyond simply being able to drive down the road, but in fact being responsible for all aspects of vehicle safety.